Hey viewers! In today's video, we are going to talk about particle accelerators. A particle accelerator sounds like something that could only be real in a science fiction movie, largely because most of us don't really quite understand how they work despite the simple physics behind them. And that's exactly the purpose of this video, because in less than 6 minutes, we will give you everything you will need to know about particle accelerators, and you will be able to understand how they exactly work and the physics behind them. Particle accelerators are the most important tools of fundamental particle physics research. The goal of a particle accelerator is to energize a particle by accelerating it with very high speed using the electric field and manipulating its direction using the magnetic field. Then, they are smashed onto a target or against another particle. This procedure can be done in two ways, either by traveling in a loop or in a straight line.
Particle accelerators are widely used in the medical field, especially in radiation therapy. The medical linear accelerator, also called LINAC, produces a beam of either electrons or very high energy X-rays. The radiation beam can be shaped and directed to match the tumor shape and consequently destroy cancer cells while sparing the surrounding normal tissue. In this case, the electron is accelerated to approximately reach the speed of light and hits at the end a heavy metal target, more specifically a tungsten target. The interaction resulting from this collision creates the X-rays by converting the electron's high energy into photons. In such configuration, the path of the negatively charged electron is controlled by a set of quadruple magnets that steer and focus to help define the electron beam. In this set, magnets are also used to bend the electron beam. This process will not only position the beam to strike the target, but will also focus the beam to a diameter of 1 millimeter. This is due to what is called achromatic behavior. This will help reduce the size of the machine and provide better conditions for the patient setup. But one of the most interesting usage of particle accelerator is for particle physics discoveries, where on the 4th of July 2012, the Large Hadron Collider in Switzerland proved a theory that dates to 1964, the discovery of Higgs boson, which is now classified as one of the elementary particles.
Now let's put some stress on the physics in behind. What happens scientifically in linear accelerators? Let's take advantage of what we have gained from physics too. Well, linear accelerators use two types of fields, electric and magnetic. The electric fields are used to accelerate the particles, while the magnetic fields are used to keep the particles in the middle of the tube. But how? Let's start by the magnetic field. The magnetic fields play the role of a guidance system. It experiences a force perpendicular to their velocity vector as well as perpendicular to the magnetic fields they are experiencing. The direction can be found using the right-hand rule. When you hold out your right hand to form an L shape, point your thumb in the direction of the velocity vector or travel direction and point your fingers in the direction of the magnetic field. The force experienced by the particle comes out of your palm. Now, for negative particles, the thumb should point in the opposite direction of the velocity vector. So, how can we make the particles follow a path without knowing where exactly they are? The answer is surprisingly simple. We create a magnetic field that is zero in the center and generates a big inward force to further the particle straight from the middle with four magnets. It looks like this. Notice that the particles that travel outside of the path in the diagonal direction will not meet the magnetic field and will therefore not be corrected. These particles will collide with the charged plates and will be lost to us. To reduce the loss, we can make this magnetic field with more than four magnets, making sure that the gaps in magnetic fields are as small as possible. Move on to the electric field. As we all know, particles are attracted to the site with the opposite charge of their own. On the other hand, they get rejected by the similarly charged plate. Based on this very simple principle, the tube is made up of chambers that have opposite charged sides. Well, what happens when a particle, assume positive, flies through the plate? Now it is in chamber 1. It will after enter chamber 2 without problems. When it will arrive there, however, the particle will be attracted by the plate behind it and rejected by the plate in front of it, which will make it slow down. The solution is very simple. The electric field gets switched exactly at the moment the particle is passing through the plate. Chamber 2 will then experience a positive charging behind and negative one in front of it, and hence it will speed up. Same procedure iterates along the whole tube.
As you can see, we can really take advantage of what we have studied in physics 2. Combining the knowledge of electric field with the one of the magnetic field helped in improving medical technologies as we saw before, but also to generate large amounts of energy. From what have been said, we see that the particle accelerator cover a wide range of scientific and engineering advances to make it the most important tool for the investigation of matter at the subatomic level. Thus, improving the use of particle accelerators have become a necessity when we look at all the achievement that it has brought to our modern world. We hope our presentation gives you a clear idea about what the particle accelerator is all about and how the course material is related to it. Thank you for watching.